In this video, we discuss particle equilibrium, which deals with particles that are subjected to forces that are in equilibrium. The particles are either motionless or have constant velocities. In this class, we mainly deal with objects that are motionless. If you recall, Newton's second law states that an object's linear acceleration is the result of unbalanced forces acting on the object. As a special case, when the resultant force is zero, in other words, there is no unbalanced force, then the object will have an acceleration of zero as well, which means that there is no change in the object's velocity, and therefore the object is either at rest or it is moving with a constant velocity. This is known as Newton's first law. Notice that in all these equations, the force F and the acceleration A are in bold letters, indicating that they are vectors. Therefore, the condition for particle equilibrium is simply described by Newton's first law, that the resultant force must be zero. For a 2D problem, since the forces are within the same xy plane and therefore each force can be resolved into x and y components, we can write the vector equation into two scalar equations instead. That the resultant force along the x direction equals to zero, and the resultant force along the y direction must equals to zero as well. And we know that with two independent equations, we can solve for a maximum of two unknowns. For a 3D problem, since each force that acts on the particle can now be resolved into three components along the x, y, and z directions respectively, the same vector equation can now be rewritten into a system of three scalar equations, enabling us to solve for a maximum of three unknowns. Here is a simple example. The three forces acting on the particle are in equilibrium, and we know force F1 and force F2 in Cartesian vector forms. We now need to determine force F3. The first step is to write the force equilibrium equations according to Newton's first law, that the resultant forces along the x, y, and z directions must all be zero. Then, into these equations, we can fill in the known information, which includes the x, y, and z components of forces F1 and F2. The unknown parameters are the x, y, and z components of a force F3. But since we have three equations, we can solve for all three unknowns. And eventually, we can express F3 in its Cartesian vector form as well. Of course, this is a very straightforward example, and in many of the practice problems, there could be other kinds of unknowns, but the problem-solving method will be similar.